Hi, I'm Antonio Sella, and in this video we are going to discuss how to compute and interpret several stability margins provided by the robust control toolbox with Matlab. In particular, we will discuss what these three commands mean. In order to keep things simple, we'll just consider an open loop second order system with uncertain damping to better apprehend what we are doing. The actual use of this is usually in the context of closed loop weighted generalized plans, etc. in robust control design, but we'll stick to this mass spring damper system to better understand physically what we are doing. So this will be the model we are going to work with. Unit gain system, in which the coefficient that multiplies s in the denominator is uncertain. Its nominal value will be 1, and we will have some interval for that coefficient. In particular, it will range from 0.5 to 1.5. We will model that with some delta real parametric uncertainty, uncertain real command of robust control toolbox. This delta will be normalized between -1 and 1. We will introduce that with this Matlab command, and indeed, this will build an uncertain real parameter with nominal value 0 and interval -1, 1. So with this, we will get this 0.5 to 1.5 interval of this coefficient. And of course, if we were going to use standard formula of the damping coefficient is this thing divided by 2 square root of 5. But we are not going to use the damping coefficient and natural frequency notation. So, how do we input this uncertain transfer function? Well, we will use this fact from theory that this transfer function is the Laplace transform of the normalized state space representation with these A, B, C, D matrices. So, our B coefficient in here will be an uncertain real number. This is not the only way of modeling this uncertain system with the robust control toolbox, but okay, we'll keep with this option. So we'll insert these matrices as follows. This 5 here will be -5, this is the minus C stuff here. Then this thing changing sign will be this part of the A matrix, the -B stuff, and then this 0, 1 is this 0, 1, this 0A gets to be 0, 5, and then C and D are copied from what the theory says. So this GS uncertain builds our uncertain model for further analysis. Okay. Know that if delta were an uncertain dynamics, say that we may account for, vibrations or some internal stuff of the damper, well, in that case, this way of introducing the model will not be valid, and we would need to resort to the linear fractional transformation framework, which is the formal, always valid way in theory. But as our delta is an uncertain parameter, the SS command swallows this uncertain matrix. So we go on. The step response is this thing that, of course, as we have an uncertain damping, then we have uncertain overshoot, uncertain settling time, etc. Robust control toolbox just plots the step response of a bunch of random plants. Nominal value recovers the nominal plant with a delta of 0, here we have it, and H infinity norm is the resonance peak of linear systems. So if we ask Matlab for the infinity norm of this nominal stuff, will tell me that its peak resonant frequency is 2.12 and the peak gain is 2.29. Our objective now, given that we have uncertainty here, is finding if there are some unstable plants in my plant family, or which is the worst case resonance peak. Of course, from undergraduate textbooks, we already know the answer. But the thing is that we are going to use the robust control toolbox commands because those commands will work in more complex multivariable cases. So let's go with the main content of this video, which is getting the uncertain model and doing some robustness analysis. So the first command we are going to use is robstab. This gives me a stability margin, and it outputs 2 as stability margin, and the worst case uncertainty is delta equal -2. So the first thing is that as this number is greater than 1, we have a guarantee that all our plants are stable. Indeed, we know that all plants in the interval -0.5, 1.5 are stable. The command tells me that the uncertainty can be doubled without losing stability, but when we double it, then we hit the stability limit, so we cannot increase it further. Indeed, if delta is -2, then this coefficient will be 0, and we will have a marginally stable second-order system with no damping, and this is exactly what we obtain here. With delta -2, we get this 0 coefficient in our transfer function, so this is the stability limit, but as delta is greater than 1, means that all our plants are stable. We have used the uncertainty substitution command, so that in this uncertain model, we substitute delta with this delta value in this worst case uncertainty output of robstab. The next command we are going to discuss, it's the worst case gain. In this case, the output of this command, first output, is the worst case resonant peak. So there is a plant in my family of plants which has a gain at the resonant frequency of 4.5, at frequency 2.2. So we have kind of slightly higher resonance frequency and double gain in my set of plants compared to the nominal stuff. The second argument is the worst case uncertainty, and if I substitute this delta -1, we get, of course, 0.5, the lower limit of our damping, which of course we already knew from our undergraduate courses, but we are happy to see that Matlab outputs the same thing. So the lowest damping gives the worst case resonance peak. And the last command we are going to discuss, its meaning, it's the robgain command. This is used if we have a gain limit we don't wish to get above it. For instance, imagine that we are designing some kind of suspension or whatever, and we wish to have a resonant peak of less than 2.8. Then, as the worst case resonance peak is 4.5, but the nominal is below 2.8, it was 2.3, then for a small enough delta, we will be inside the required limits. And this command tells me which is the reduction of uncertainty that keeps me below this limit. This 0.375 tells me that I would need to be sure that my uncertainty is reduced to 37.5% of my original interval width in order to be sure that my resonance peak is lower than 0.8. So with this uncertainty, if I substitute this delta, I get this thing with 0.81 as a worst case uncertainty, but keeping below this gain limit. So as this number is less than 1, we don't have, let's say, robust performance. We cannot guarantee that the gain is below a given limit. But this tells me how much I should shrink the uncertainty ball to keep below that limit. In here we have put 2.8, but in most robust control problems, once normalized things, this gain limit is 1 in most cases. But okay, we are not dealing with that at this moment. So let us graphically plot the output of these three commands to finish understanding what we are doing. If I plot the nominal, the worst case gain, and the limit gain 2.8 uncertainties with some y lines with the bounds computed by worst case gain, the h infinity norm of the nominal system, and my 2.8 gain limit in decibels with this 20 log 10, then there I have in blue the nominal plant and its nominal h infinity norm, in red the worst case gain bound and the plant achieving that thing with the lowest damping in my interval, and in yellow the worst case plant that achieves my arbitrarily set gain limit of 2.8 obtained with the robgain command. So these are the both plots and y lines of the outputs of the three commands we have analyzed. Of course, if I tell the robust control toolbox to throw the dice and show the Bode magnitude plots of a bunch of random plants, then all of them will be, of course, below the worst case gain, but some of them will be above the nominal one and above the limit gain for robgain 2.8. And we will have also plants with more damping than the nominal one, because we have an interval. Damping can be larger than 1, and those ones will have a lower resonance peak. So in this case, let's say friction works in my favor. But robust control does not consider the best cases. We always concentrate on proving some performance resonance peaks, in this case, for the worst case situation in my uncertain family of plants. So the only important things are the ones we plotted before. To summarize, in this video, we have discussed the meaning of the robustness margins provided by these three robust control toolbox commands in a second order system with uncertain damping, and we have analyzed the outputs of those commands both numerically as stability margins and in the Bode magnitude diagram looking for the resonance peak. So we finish here. Thanks for watching.